The first model of volatility clustering we're going through is the ARCH model, the autoregressive conditional heteroscedasticity model. And we have this autoregressive distributed lag model, just to take a simple model. And we have this regression model in which the lagged value of y is the autoregressive term, and the lagged value of x is the distributed lag term. And in this case, the volatility around the regression line is captured by the error term. So the error term has an expected value of 0, but in our previous models, we have assumed that the volatility or the variance of the error term has been a constant. Not so in this scenario, because here the conditional variance of the error term, given its past values, is modeled, or not modeled, but expressed as the variance at time t equals the variance of this error term at time t, given its values in previous periods. If we assume that the variance of the error term is constant, then we could just disregard any previous values of the error term and just say that this variance is constant over time. But we have seen in the previous slide that, for example, the daily percentage changes, the volatility of these changes and the magnitude of these changes, it's not constant over time. So to model this, Engel in 1982 proposed to model this variance by using a distributed lag model of order p. So this variance of the error term is a constant which is there no matter, which is a variance level, which is there no matter what happens to the error term, and plus the squared error terms as lagged variables up to p lags. And actually quite interesting is that this equation 1 here, it does not contain an error term. And the reason why we do not contain an error term here is that this relationship here is assumed to be deterministic. So if you know the values of the squared residuals in p previous periods, then you know exactly, or we are assuming that we know exactly the conditional variance of the error term at time t. So that's why we do not have an error term in this ARCH equation. In our case, we have p number of lags of these squared residuals, and this is called an autoregressive conditional heteroscedasticity model of order P. So we just write it as arch P. And if the alphas in this model are positive and the recent squared errors are large, and the squared errors are large if there has been a large positive or negative error in this model. If the squared errors are large, then the arch model would predict that the current squared error would be large in magnitude for time t as well. So this model, if the alphas are positive, this model would predict that small errors follow small errors and large errors follow large errors. And in this case, we have used the ADL11 model as our base model, and we have used an arch P model to model the variance, conditional variance in the error term, but the arch model can be used to model the conditional variance of the error term in any time series model.